Okay, here we go. Homework spirals. Section 10.3, ellipses. That homework's due today. I was going to turn off the light, but I think we're okay. Let me just zoom in. That might help a little bit. Because these answers are kind of small. Okay, so for number 6, it matched with C. Or for number 8, it matched with D. For number 14, you were trying to make standard form out of the clues that they gave you. So HK was just 0, 0. You have your standard form, but you needed these two measurements. Your plus or minus 2 told you that C was 2. Your major axis, remember, that's the whole thing. Cut it in half for the radius. How'd you guys know that 25 was supposed to go under the x squared and not the y squared? Well, but couldn't it have been major in the vertical position, not the horizontal? How do we know it was horizontal? Good, the foci. Because the foci were horizontally apart. Oh, so the major axis had to keep going horizontally. And then use your little formula to find 21. Square root of 21 was b, so then 21 was b squared. There's another one, right? Number 26. Give you a second. You're plugging in the clues. You should have ended up with the final standard form below. The one weird part might have been when you went to go plug in your A, which ended up being 3/2. Because the distance from the center K to the vertex K, that's what your C, not your C, sorry, your A would have been your major radius. The distance from the center to the outer edge, and that ends up being 3/2. And when you went to plug it in, yeah, 3/2 does go in the A spot. It is going to be vertical because the K is what's changing. However, when you square that 9/4, it's going to look a lot nicer if you multiply by the reciprocal. So that's what they did down below. Let me see if I can zoom out just enough for you guys to be able to see both of them at the same time. I can almost see it. Which one was prettier, 38 or 48 to start with? 48 looked nicer, except wasn't the work a lot harder? I thought 38 would be easier to start with, right? Because who's your center? Oh, -3, 2, right? Your major radius, oh, 4. Who's your minor radius? Root 12, which is 2 root 3, some decimal-y thing. And then you could have taken all those and made a picture from it, right? Found your vertices by measuring over the 4. Nope, that's vertical. Up the 4, down the 4. Foci, finding C by plugging in the rest. Measuring up 2, down 2 for the foci. Eccentricity takes C over A. This one was super nice and set up and ready to go, even though the root 12, that made it a little bit messy, right? Made it a little bit messy, but not impossible. But 48, what did you have to do to even start? Get it to standard form. So you had to do all this work first. Like we saw yesterday, move the 60, group the x terms together and the y terms together. Don't pull out an x or a y, but do pull out the coefficients. Complete the square. So they added in a 4, added in a 1. 4 and 9 made 36. 1 and 25 made 25. Then they put it all together. Lucky ended up being 1 without having to do any more work. And that's when it got weird. Did anybody think it got weird right away? Because, yeah, there's nothing to divide by. Like, what do you... So instead of dividing by to get your coefficients to reduce to be a fraction, you had to actually make a fraction. Instead of multiplying by a number, dividing by its reciprocal. Instead of multiplying by a number, dividing by its reciprocal. And so... if you take your fractions 1/3 and 1/5 when you square root, the minor radius 1/5, it was tiny. Look at this little guy. And that's by going units of 1. Radius was up 1/5, down 1/5. Its major radius was over 1/3, back 1/3. It was a little baby guy at 1. So you guys can see the rest. But I had to take this 9 and 25, had to show it with division because right now this isn't standard form until you make the division. I think that's the last even. So go ahead and stop me if there's something, or ask me if there's something you want me to explain a little bit further. Are we letting fractions scare us off? Okay. A little bit, that's just being honest, right? So just persevere through. Or this root 12 up here, that was a little bit nasty. The fractions were a little bit nasty. But you guys can do fractions. It's all right. Hang in there, persevere. Don't just go straight to your calculator. Okay, any questions on odds? Those were the evens. We're all right? Okay. You guys would let me know if you're not? All right. Remember, be real. Here we go. Section 10.4. The more time we can spend on this, the better. So I am totally cool just going straight to 10.4. Because hyperbolas, think parabolas and ellipses combined. Think parabolas and ellipses combined. Think parabolas because we're going to have to be going from a vertex to a focus that's going to be inside a branch that kind of looks like a parabola. And we're going to have things like an axis of symmetry, but we're going to call it a transverse versus a conjugate axis. Anyway, we're going to talk about some axes, which we didn't really have to do with ellipses. But think ellipses in that we have a standard form that's going to look like an ellipse standard form, and we have this whole C measurement. We're going to have to kind of put the two together. Huh. Okay, well, that's not going to work. Let me go ahead and move that back to where it's supposed to go. Guys, hyperbolas can show up two different ways, so we're going to fill that in just a second. But first of all, let's make sure we understand what's going on. I'm not going to go super crazy with trying to show you guys visually as to where hyperbolas come from. There is a special relationship where if you take or make a right triangle, whether it's to one branch or to the other, using the distance between the two foci as the bottom, the D1 and D2, D1 plus D2 will always be constant. Ooh, no, it's the subtraction. I apologize. D2 minus D1 will always be a constant. It's a lot more complicated than the ellipse, though, as far as how to visualize that and how to show that. Because adding, I could just do like I did with the ellipse on the board, but with subtracting, it's a little bit harder. But the idea is there is still a certain relationship, and that relationship is dependent. The branches actually are generated from this distance between the foci. But let's just get down to the shape itself, the hyperbola, the conic section itself. You guys notice a few things that are the same. For instance, A was the measurement from the center of an ellipse to what? The vertex. Except with an ellipse, it was enclosed. It wasn't going out. With hyperbolas, the branches are going out or away from the center. But we still have A being the measurement from the center to the vertex. Just now it's going to be the vertex of a branch, like a parabola sort of, and the vertex backwards to the branch. So we still have that A measurement going out from the center, just the shape is different. And we still have C going from the center out to the focus, but what's different about the focus with hyperbolas? It's farther than the vertex. Good. For ellipses, where were the foci? Inside, which is why we needed A squared minus B squared, because we need it to be less than A, enclosed in A. But for hyperbolas, it's going to be A squared plus B squared, because I need it outside since the branches are going away. They're not enclosed in like an ellipse. So a lot of the formulas are similar in the sense that we still have an HK as our center. We still have vertices. If it's horizontally, the hyperbolas are horizontally oriented. Think it looks like an X a little bit. If they're horizontally oriented, we're going to be adding and subtracting to the H, keeping the K the same. Same thing for the foci, adding and subtracting the C. So the formulas are super similar, just we have to remember, okay, the shape is going to be a lot different, and the foci are going to be outside. So let's sketch a vertically oriented one, and I want to see if you guys can use what you see to fill in the formulas for center, vertices, and foci for the vertically oriented ones. So vertically, everything is super similar. I would naturally probably flip it around the other way so that the C and A go up, except most of us can turn our heads to the right a lot easier than turning to the left. Although, is anyone left-handed? Not in this class. I wonder if they can turn to the left easier. It's a good question. Wouldn't most of you guys say you can turn to the right a little bit easier, like to look at something? Check it out. The left hurts. I don't know. Really? The right's tight? Wait, you're going to the left. That's to the left. That's to the right. Yeah. Oh. All right, maybe it's just me. For me, it's easier to go to the right. Anyways, you're trying to fill in the formulas or the reminders for how to find the center, how to find the vertices, how to find the foci of a vertically oriented one. And if you guys are noticing, there's also a new vocab word. It's called the axis of symmetry for parabolas. It's called the major axis for ellipses. And what's it called for hyperbolas? Transverse axis. Transverse axis. Do you think? Could be. Like what you sleep on more naturally? Oh. So like both of them are uncomfortable? Strung up by your feet? That'd be fun. Okay, I'm going to pause for a second because the poor people who are absent don't thinking. That's something. You disproved my hypothesis of right-handed, left-handed, which way to lean is easier. So there you go. Or maybe some of you are more naturally ambidextrous. Ooh. Maybe not. Okay, center. What do you guys think? Yep. That one's the easy one. Still HK. Nothing changed as far as the center. How about the vertices? Good. H, yeah. You need to get the plus or minus because remember we're going, oops, not plus or minus K. Oh, I have it there. Look, it's just chilling. Oh, that doesn't work. I have the wrong ones there. Ignore. There we go. And what's the foci going to be? Have you guys gotten the pattern of what's going on as far as when we add to the y's versus when we add to the x's? And it's a lot easier. Remember, you can memorize every single one of these formulas with like charts and tables and illustrations and diagrams. But if you can understand the idea, oh, A, center, out A, back and forth, or up A, back and forth. Hey, that gets me my vertices. Center, out C's or up C's are going to get me my foci. It's just going to make all the difference in the world if you can visually grasp it. And if you can't visually grasp it, that's just how your brain learns, and that's okay. You're going to maybe need to do more memorizing. So let's go ahead and go do some examples, because you guys know this can get interesting. Let's make sure there are no other formulas that we need first, though. Joop, 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 and go. Ooh, we never wrote standard form. Lo siento. So from all the above, we just figured out how we're moving A, how we're moving C. Interesting. There wasn't a B on the picture, was there? Huh. For parabolas, there was only a P. There was only one measurement for us to really deal with. So we didn't stress too much. If we wanted to figure out how wide the parabola was or how narrow, we could find zeros or a couple points and follow the symmetry of the parabola. For ellipses, it was actually even easier to make the shape because with ellipses, the major radius helps us one direction, the minor radius helps us the other, and we just connect because it's enclosed. The hard part about hyperbola is it's not enclosed. And since it's not enclosed, well, A gets us to the vertices, C gets us to the foci, but what actually gets us the branches as far as how extended, how narrow, how broad they are? Yeah, we need to talk about B. And not specifically the space. You could kind of go back to that. It's technically the space is the square, right? But that B does have meaning. And as Colby was saying, he's saying, okay, the distance between the vertex and the foci, depending on how much space there is, will determine the actual narrowness or broadness of the branches themselves. The actual curvature, we could put it that way, if we want to be snazzy, the actual curvature of the branches. But to help us find that curvature in an easy way without just having to find lots of points and then follow them and see what the curvature looks like, or without having to memorize something like eccentricity and exactly what types of shapes will come from the different ratios between A and B, there's an easier way. And the easier way is think about asymptotes, because every hyperbola has asymptotes. We're actually going to go back to those figures that we just drew and add in one piece that you technically can't see and yet is very important to the actual conic section themselves. Every hyperbola does not just have a center, does not just have vertices, does not just have foci, it has branches, and those branches technically skim asymptotes. It's not like a parabola that just keeps on extending outward for forever. Hyperbolas are actually held within asymptotes. So they're similar to parabolas, and yet they're held within. And if it's vertically oriented, guess what? As long as everything else is the same, even though the orientation will be different, you're going to have the exact same asymptotes. You can think of them as oblique asymptotes, but we're not going to find them the same way as we found oblique asymptotes. There's a simpler way. So the nice thing is you guys realize when you drew the picture, the asymptotes aren't actually drawn, but they can be used to help us out with the curvature. And how we're going to use them to help us out, if we come back to this page for just a second, the slope of the asymptotes will always be plus or minus I can't put B over A because depending on the orientation of the hyperbola, if you guys notice, the B squared always stays in the second term, which is sometimes Y's and sometimes X's. The A squared always stays in the first term, whether it's X's or Y's. So we do need to think about M is going to equal plus or minus rise over run, which we already know. Which is going to equal plus or minus the coefficient, and technically we could say the square root of the coefficient under the y, all over the square root of the coefficient under the x. So if we use each of these, technically on this one, the asymptotes for my hyperbolas are going to have, or going to intersect at HK. Because if you guys missed it down from below, they always intersect at the center. You can always start them at the center and then follow the slopes to get more points. And this first one, M is going to equal plus or minus the y coefficient, which would be b, or the square root of the y coefficient, which would be b, over the square root of the x coefficient, which would be a. But in this one, how would that change? Exactly. The asymptotes will still intersect at HK. But this time my slope is going to equal plus or minus. I need, once again, the coefficient, or the square root of the coefficient under the y. That needs to go on top, and then the square root of the coefficient under the x on bottom. So that's why I'm not just going to give you one, I'm going to show you both. But the nice thing is the pattern still remains the same. You still need the rise over the run, so you're going to use, okay, to the y, that always has to go on top. Whichever one is attached to the x, that always goes on bottom. But that begs the question, okay, wait a minute, what is so different about these formulas up above? For ellipses, it was no big deal. Just whoever's the bigger one, that's the major axis. Whoever's the smaller, as far as the denominators, is going to be the minor. But on this one, what do you guys notice is in between both of these standard forms? Subtraction. What was in between for ellipses? Addition. So for addition, it didn't actually matter which way it was written, because a plus b is b plus a. But the problem is, does the subtraction make a difference for hyperbolas? And the answer is yes. So I can't always have this guy be first because sometimes he's going to need to be the negative one. So let's think about this. In this first one, the x term comes first, and how is my hyperbola oriented? Horizontally. So this one, if the x term comes first, term comes first, I'm going to have horizontal orientation. So everything from the center is going to move horizontally. My h's are going to be adding and subtracting the a's, adding and subtracting the c's for the foci. Then I'll just need to be using the b's in order to go ahead and help me out with my asymptotes. So, quick word to the y's. Whichever term comes first is the orientation you're going to follow. So who comes first in the second one? And whoever comes first, it's going to be the orientation. My y variables denote the vertical measurement, right? My x quantities denote the horizontal orientation. Okay. So with that, let's see if there's anything else super crucial, because we didn't even know there were asymptotes until we got to this page. We're like, oh, well, we got to talk about that. Let's talk about the standard form. Whoever comes first is going to totally determine what type of hyperbola, what orientation of hyperbola I'm doing, and the subtraction makes it a hyperbola. What do you guys think will happen if this one ever disappears in all of our work? What if it becomes like a 0 or a negative, remember? There's a word for it. Degenerate. Yeah, it's going to be one of those degenerate. Yeah, if something happens, like, that degenerate. Now, make sure that you did the work correctly, but it's going to be a degenerate. Hey, kiddos, check it. Check it. Check it. What are we going to do? Play. Here we go. Let's play with examples, just like we did with ellipses and parabolas. I want you guys, before you do anything else, write it down. Good. And then the first things I want you to do, just follow my method for just a second. As soon as you write these down, I want you to graph the points and then figure out which standard form are we going to use, the one with x in front or the one with y in front. Graph the points and choose the standard form that we're going to try to make it match. Let's do a quick vote just really quickly. How many of you guys would say that visually seeing something and how it works helps you understand it better? How many of you guys say that visual helps? Visualizing helps? Interesting. About half, a little bit more. Okay. So once again, I totally admit some of you the visual might not help as much as just memorizing, but usually the majority seeing helps. Do you guys graph the points? Check in your groups. After you graph the points, do you agree with the standard form you should be using? Hold on, pause, check. Did you choose the right standard form? You guys agree? Has to be that one. Someone explain why.
We're not moving y's. The transverse line is that y equals 2.
Okay, so some of you guys can actually see just in the points that the y's stayed the same. So you're like, okay, well, the axis must be y equals 2, so therefore everything's changing horizontally. Maybe you didn't even need to graph. Maybe the numbers kind of told you enough. But for others of you, when you went to graph, and when you got the foci to be negative 1, 2, and 5, 2, 1, 2, 3, 4, 5, the vertices 0, 2, and 4, 2, hopefully you realize, oh, the only way this works is if my branches are horizontally oriented. Now we don't know exactly how horizontally oriented, but hold on, we got to fill in some stuff. What's a measurement that I know just by what's up here on the screen? C, yeah. C is going to be the distance between, well, I can't really figure out C until I, remember, C is not in between here. C is from the center out to the focus. So I need to figure out first, where's my center? Where's my center? Good. Some of you can visually figure out, oh, halfway between 0 and 4 is 2, 2, and that's totally true. The other way is you could have done the midpoint formula if you wanted for the center. If it was ever not this pretty or not this nice, you could have done 0 plus 4, 2 plus 2, and you would end up with 2, 2. So that's my center. We're building. Okay, now Colby, what would my C be now that I know the center is 2, 2? I need to go 1, 2, 3. Good. So C is going to equal 3. Someone tell me another measurement I now know. A. What is A? Mm-hmm. So I can say the A, which is the distance from the center to the vertex. Oh, that's cool. So I can plug in A. Oh, where do I plug in C? I need my formula. C squared, remember, comes from A squared plus B squared.
That's going to be an ugly number.
9.
I gotta jug it like this.
Wait, but I don't need B. Don't I just need B squared? Oh, it's not that bad. Just put in 5. So, is this right? And the answer is yes. Now, could they ever show this to you in a different form, though? Yeah? How could you take this and work backwards if you were trying to give someone else in honors pre-cal a really hard practice problem? How could you make it harder? You wouldn't give them this, would you? Wouldn't that just give them everything? How would you make it harder? Well, maybe giving them the clues, but let's assume that you're going to have them get the sketch, like you're going to have them find all the information. No, let's say you're doing this exact same problem, yeah, but what form would you put it in to make it harder? And what would you need to do to get there? Multiply both sides by 5? Maybe. Multiply both sides by 4? Maybe. How about multiply both sides by 20? Wouldn't that be smarter? Because then you could go ahead and change this, multiplying both sides by 20. Now what would you do to make it harder? Subtract the 20 and FOIL all this out, right? So you could go ahead and simplify and FOIL, and you would get to your ax squared. Ooh, do you guys see it would be a minus by squared? Remember, they might give it to you in this form. You need to know how to get backwards in order to be able to find all your characteristics. Just reminding you how to go from one form to the other. Because you've had to go from here backwards for ellipses. Just reminding you for hyperbolas, it's going to look so similar, but what's going to be different? The minus. Ready, set, play. If I were you, I would graph the points first to figure out which standard form. You can work in your groups. You can hash it out. Let's see how far you can get. I'm going to freeze the screen so you can't see what I'm doing, and from time to time I might reveal little bits and clues.
I wouldn't even listen to you. I just go
There's a few clues. Which standard form in the center? Maybe you guys already figured that out. Maybe visually, maybe just thinking about the numbers. Does it make sense that the center is the midpoint of the vertices? Does that make sense? Okay. Does it make sense why I put the x term first? Because what's changing up here? The x is, so it's horizontally apart. Good, good, good. What's your a going to equal? But what's b and what's c? How? They didn't tell us that was the focus. Oh, they just told us it was a point. Because look, it's not on 1. Realize that this is not on the transverse axis, so it's not a vertex, it's not a center, it's not a focus. Well, what is it? I don't know, a random point. 1, 2, 3, 4. Let's go 5. 1, 2, 3, 4. This is a point on the branch. Okay, so David's thinking of, well, can't we think through that whole D2, D1 and how we make a triangle? And it's actually easier than that. But let's plug in what we have. Let's plug in what we have. Because the problem with your distance thing is we're going to do distance formulas with multiple. And without having the focus, we'd have to make it an unknown x and unknown y, which gets really messy. Because we'd have 2 unknowns. But check out, what if we plug in what we do know, which is x minus 0, right? Squared. All over, we know a is 2, so 2 squared will be 4. Minus y minus 1 squared. All over, we don't know b. Some of you are like, well, now you don't know 3 things. Okay, but pause. Doesn't this equation need to work for every point on the hyperbola? Isn't the definition of a function of a graph the set of all of its points? So can't I take this x and this y and say, okay, maybe you're not a focus or a vertex or a center, but you're an x and you're a y and you have to work in this. And what happens if you plug in the x and the y? Simple algebra solves for b. Plug it in, and start playing, because you have to move some stuff around and solve. Yeah?
Would it work if you drew the triangle and then found a, b, and c through the, what's it called, Pythagorean theorem?
So using the formula c squared equals a squared plus b squared.
Or just be finding b, so you already know that.
Well, we need to draw it to the focus. It's unknown, right?
Yeah.
And then we have to somehow do this.
And then the vertical line would be 3 because.
So this would be D2. This would be D1. This would be my C. We could make D1 equal to 3 since we know that measurement. D2, you could do the distance between 5, 4, and 0, 1, right?
Yeah.
And then you could use Pythagorean. No. Is Ryan right, though? No, well, he's saying we can use that whole idea of D2 and D1, and then that's the focus, and this is C. We can use the idea, if you go back to the original definition, that we didn't really work as far as how to draw it. But pause. What's the problem? We don't draw from the center to make a right angle. We draw from the, So it was a good idea, but the problem is we can't draw it to here. We'd have to draw it. We still draw the focus. We could still make this our D1, which equals 3. We could still make this our C, but the problem is we have to go over here and draw. So do we know this? No, that would be 2C. And do we know this? No. So that's the struggle as to why we might not want to use that definition. But if we come down here and say, oh, wait, it's just a point. Plug in the 5, plug in the 4. Can we solve for B? Yeah, we can. All right, cool kids. You're just missing some homework help. I'd say tackle this homework tonight, get as far as you can. Let's go over a couple more examples and maybe even do homework questions tomorrow. Bye, guys. Don't forget test corrections by the end of today if it's not in already. 9,000.